Good afternoon, everyone. Welcome back to the cycle of seminars of the astronomy department at IAG-USP. And today we have the pleasure to welcome our first speaker of the year, which is Dr. Breno Raphaldini. Thank you, Breno, for accepting our invitation, first of all. And Breno got his bachelor, his master's, and his PhD at IAG-USP itself, but interestingly, from the Department of Geophysics. And now he is a researcher at Durham University in the UK, working in the Department of Mathematical Sciences. And the seminar that Breno has prepared for us today is the topology of magnetic fields in solar active regions. And questions to Breno will be addressed after the presentation. And if you are following us from the YouTube channel, the seminar, the questions will be asked also after the seminar. I will redirect your questions to Breno. And before the seminar begins, I ask all of you here at Google Meet to mute your microphones and turn off your cameras. And having said that, Breno, you can start whenever you're ready.
Okay, so thank you for the invitation, for the organizers, Reinaldo and Maria. And so today I'll talk about the topology of magnetic fields in solar active regions. And I'll begin introducing some basic facts about the magnetic activity of the sun, and I'll introduce some quantities that are useful in the study of magnetic fields in the sun, such as the magnetic helicity and winding. And I'll show that this quantity, the magnetic winding, which is related to the topology of magnetic fields, can be used as an indicator of flux emergence and explosive events in the sun, such as solar flares and coronal mass ejection events. So, as you know, the sun is a star that the interior of the sun is composed by several layers. So here you have the radiative zone that rotates as a solid body, and above the radiative zone there's a convection zone, where we believe that is the place where the dynamo of the sun operates, which means that this is the place where we believe that magnetic fields are generated in the sun. So in particular, the magnetic fields generated in this region emerge from time to time, generating emergence of magnetic field structures in the solar photosphere that can have many effects and can be observed. So as the magnetic activity of the sun is characterized by a 11-year cycle that can be observed, for instance, in the number of sunspots at a given time. So here you see a time series of the number of sunspots in the sun. You see that it follows more or less a periodic pattern, peaking at every 11 years, more or less. So what is a sunspot? So a sunspot is a result of the emergence of magnetic fields through the solar photosphere. So here you can see a schematic view of a prototype sunspot, which is composed by two foot points from where the magnetic field lines emerge. So, and this is a view of the sunspot here. So in sunspots in active regions, which is the area where the sunspots arise, might cause also explosive events such as solar flares and coronal mass ejection events. And these events are very important because they may cause several effects on Earth, such as they might cause problems in telecommunications. They might damage satellites, cause problems in energy transmission, and also several environmental problems. So it's of great interest to understand and predict these events. In particular, solar flares are eruptions of electromagnetic radiation in solar active regions that are originated by the release of energy through magnetic reconnection. And the intensity of these solar flares are measured by the peak of flux measured in watts per square meter, and they are classified in 5 classes from A to X, being A being the smaller ones and X the most intense ones. And this classification is in log 10 scale. So here you can see, for instance, series of solar flares in one particular active region, and you see these horizontal lines here are the thresholds for the intensity of the flare. So here is all the ones that are above this threshold are C class. When they go above this threshold, they are M class, and when they go above this threshold, they are X class flares. So in particular, M and X class flares can cause many of the effects that I mentioned before, such as problems in telecommunications and damaging satellites and so on. So in order to study these events, and in particular the magnetic fields in solar active regions, a quantity that it has been used before is the magnetic helicity. So magnetic helicity is defined as the integral of the product of the magnetic vector potential and the magnetic field. And it's an important quantity in magnetohydrodynamics, because this quantity is conserved by the dynamics in the case of ideal MHD, which means that when dissipation is neglected. So there's a topological interpretation of the helicity, which is it means that it's the average Gauss linking number between pairs of field lines weighted by field strength. And this means that if you see here in this picture pairs of field lines, and they get entangled, and the Gauss linking number is the number of crossings of one field line through the surface defined by the other field line. So the helicity, the interpretation of the helicity is the Gauss linking number average weighted by the strength of the field lines. So in order to use helicity to characterize the magnetic fields in solar active regions, we need to calculate this quantity in a 3D region, in a volume. But measurements of the magnetic field in the sun are actually taken from the surface. So we need to adapt this in order to be able to compute this from magnetogram data sets. So this leads us to the concept of relative helicity, which is the helicity measured relative to a basic state that is a potential magnetic field. So in order to calculate the helicity, the relative helicity, we can derive, we can take the derivative of this expression and the time derivative, and calculate the fluxes of helicity through a surface in the solar photosphere through which the magnetic field emerge. And we arrive at this expression here, where B here, Bn, is the normal component of the magnetic field, and U are the velocities of the foot points of the magnetic field lines moving through the photosphere, and X and X prime are the position of these foot points on the solar photosphere. So we can also compute from this formula. We can split the velocity of the magnetic field lines into two parts. The movement through, that is vertical. I mean, when the plasma is moving vertically, and when the component due to horizontal motion, which are these two components. So how one can use this quantity to characterize the magnetic fields and the activity in solar active regions. So here is an example here from this paper from 2014, where they compute the fluxes of magnetic helicity in one active region here, and it shows here one solar flare happening when there's a change in behavior of these fluxes here, fluxes of helicity. So what's one of the problems with the helicity is that it's weighted. This quantity is a measure of the topology of the magnetic field, but as I mentioned before, it's weighted by the magnetic field strength. And when we observe the distribution of magnetic field intensities in solar active regions, we see that it's very concentrated. Here you see in one particular active region, this AR956, the distribution of magnetic fields, the magnetic field strengths, the intensity of the magnetic field, and you see that it's very concentrated, which means that this average quantity will give a very large weight in these regions. Indeed, when we calculate the helicity, the helicity densities, we see that they are very closely correlated with the magnetic field intensities here, which means that they're stronger where the magnetic field is also strong. So one alternative is to, instead of weighting this quantity by the magnetic the intensity of the magnetic field, to normalize this in a way that you put 1 here instead of the intensity of the magnetic field. And this leads us to the concept of winding, which is very similar to, has a similar topological interpretation compared with the helicity, but it's no longer weighted by the magnetic field strength. And the topological interpretation of the winding is a measure of the entanglement of the magnetic field lines, and as in the case of the magnetic helicity, it also can be decomposed into the winding due to horizontal motions of the plasma and the winding due to vertical motion of the plasma. So how can we apply this in order to understand the emergence of magnetic fields through the solar photosphere? So here I show one example of recent work from us, in which we use the magnetic winding to distinguish between models of theoretical models of magnetic the emergence of magnetic fields through the photosphere. So what we observe in emerging magnetic fields through the solar photosphere is that they are twisted. But up to recently, there was no clear evidence whether this twist of the magnetic field occurred post emergence or pre-emergence. Although some theoretical works suggest that the twisting of the magnetic field lines, such as it's shown here, is necessary for the magnetic for the coherence of flux tubes. Otherwise, the flux tube could be disrupted by the turbulent motions in the convective zone. So here in a recent work from us, we applied the magnetic winding to distinguish between the two possible mechanisms: the post-emergence twisting of the magnetic field lines and pre-twisting. So how can we do this? So here we compute, we did an MHD simulation of a magnetic flux tube emerging through the solar photosphere with convective motions. So here we show the flux of magnetic winding through this surface that represents the solar photosphere. And we see that the total winding, this blue curve, is dominated by the emergence term, which is the component of the winding due to vertical motions. So this means that this flux tube is the twisting of the field lines occur before the emergence in this case. So this is just a test to see if the winding is able to capture this pre-twisting of the magnetic field lines. So we also apply this in observations of magnetic fields in active regions, and we see that indeed the winding is also dominated by the vertical component of the plasma motion here, suggesting that that indeed the twisting of the flux tubes occur before the emergence of the magnetic field lines through the photosphere. And here we see how the distribution of the magnetic winding is in this particular active region. So here we have in green the foot points, the points of intense vertical magnetic fields. These are the foot points of the sunspot, and the strong winding occurs in between the foot points, which is the place where the tube of magnetic field lines are first emerging, in between the foot points. So in contrast here, we see that the helicity is actually dominated above the foot points. So we proceed with another application of this technique, and the idea is the following: we can now always decompose a magnetic field into a potential component and a current carrying component. So a potential component of this is just an application of the Helmholtz decomposition theorem. The potential component of the magnetic field can be derived from a scalar potential, and what's the relevance of this is that the potential magnetic field doesn't have current associated, and therefore there's no ohmic heating associated with the potential part of the magnetic field. So in events such as solar flares, there's intense dissipation of the field because the magnetic reconnection is taking place to release energy in this process. Therefore, the important component of the magnetic field must be the current carrying one. So from our observations of the magnetic field, for instance, the radial magnetic field of the sun on solar active regions, we may reconstruct the potential field by solving a Laplace equation. So having this decomposition in hand, we can analyze the the components of the magnetic helicity due to potential and current carrying parts of the magnetic field. And there are some works based on simulations indicating that flux emergence is occur when the helicity is dominated by the current carrying part of the helicity. This is from work from Pariat at 2017, and this idea, which when they actually defined a ratio between the total between the current carrying helicity and the total helicity, and they proposed that when this ratio go above certain threshold, there's a large likelihood of strong solar flares. For instance, here for a particular active region here, where this is an M-class flare and this is an X-class flare, and then they compared it with another one without any intense flares, and this quantity doesn't go above the threshold. So we inspired by this idea, we went to decompose the winding also in its current carrying and potential components, and analyze magnetogram data from active regions to see whether we can relate the behavior of these components of the magnetic winding with the behavior of the active region in terms of its solar flares, in its flares. So first, we apply this decomposition for this active region that presents no flares at least above C class, and we see here the potential component and the current carrying component, and we see that the potential component is actually larger than the current carrying one, and this could be an indication that in active regions that don't present large activity, the potential part of the winding is dominating. So here we calculate the differences between those two curves. Here we see that it's actually being dominated by the potential part, where you actually take the difference between the current carrying part and the potential part. So we apply this for another case of an active region that is very prolific in terms of the number of flares, and also the number of flares and also intensity. So this active region had 4 X-class flares, 27 M-class flares, and 55 C-class flares. And also among the X-class flares, 2 of the most intense flares, the 2 most intense flares from solar cycle 24, which was this was in 2017. This active region were from this active region, which is one X9 flare and one X8 flare. So here we compute the 2 components of the magnetic winding. Here the current carrying component and the potential component here. So you see that in magnitude, so this is negative and this is positive, but in magnitude the current carrying part is much more intense. And when we calculate the differences, we see that indeed this the dominance of the current carrying part. So this and when we observe this, we see that there's a very steep increase in this quantity that is the difference between the 2 components of the winding, and this suggests that the derivative of this curve has a very strong positive period around this time here, and we define this this quantity that is actually the derivative of this curve here. It's the difference between the current carrying and the potential part. So when we apply this difference, which we called the winding imbalance for a non-flaring active region, we see that it's mostly negative here, and it presents no flares, as I mentioned. So this is from a work that was published last week, actually. So when we calculated for another active region that presents a very mild activity, which is only one C-class flare, we see that this quantity is actually positive. But we see also that there's a bump of positive input of this quantity just before the flare here. Now we proceed to another one, this active region 11518, that presented one X-class flare and four M-class flares, which is we can say that this is an active region that is more prolific in terms of the intensity and quantity of flares. And we see that there's a very steep positive input of current carrying winding here, which precedes the start of the activity. So here in gray we show the period in which the flaring activity starts. It starts here, but it starts with a C-class with a C-class flare, and then we show here in yellow the M-class flares, and in purple the X-class flare. So here we see that this bump of positive winding imbalance precedes the X-class flares by about 50 hours. And we also see that there, just before these three M-class flares, there are peaks of in the input of current carrying winding, and also here we see that there's a spike in this quantity a few hours before this flare. Now we proceed to this other active region that is the most prolific from the solar cycle 24, which is the one that I mentioned before, which is this one. So this active region presented the 4 X-class flares and 27 M-class flares. And here we show only a few of the most intense M-class flares because there are so many. And the X-class flares are here. So they're actually here in purple. There are 2 consecutive X-class flares, one X2 flare and one X9, which is the most intense flare from the solar cycle 24. And we see here that again this pattern of a bump of imbalance of magnetic winding occurs preceding the start of the activity here in gray, and also preceding the strong flares here. And also we see that before this pair of X-class flares, we see a very large spike in the imbalance of magnetic winding, indicating that a very sharp and rapid input of magnetic topology leads to the release of energy through magnetic reconnection that is associated with these flares. So I'll proceed to the conclusions. So we showed that the winding is a useful tool in the analysis of solar active regions. We provided evidence using this quantity that the model of emergence of magnetic flux tube, in which the twisting of the magnetic field lines occur before the emergence, is actually correct, at least from the active regions that we analyzed. And we did this for several active regions, and we didn't see any active region showing post twisting. And we also showed that the magnetic winding is a promising tool as an indicator of imminent strong flares in the sun, which is important for the prediction, because these events can cause important effects such as damaging satellites and so on. So here are some references. So just to recent papers applying these concepts in the first one in the mechanism of twisting of in magnetic flux emergence, and the second one in the application to prediction of solar flares. So I'd like to thank again the organizers, and I'll stop sharing here.
Thank you, Breno, for
how can I stop sharing?
Yeah, I guess you can keep sharing. If someone has any questions to specific slides, you can.
Okay.
So first of all, I would like to thank you, Breno, for your presentation. And I'll open the questions with a question from Professor Reinaldo, actually. Go ahead, Professor.
Hi, Guilherme. Hi, Breno.
Hi.
Can you hear me?
Yes.
Yes, it's perfect.
Seconds. Sorry, I was switching the equipment. And I'm really curious about you investigated you showed the correlation between this quantity, the winding, right, and the emergence of the solar flares. So this implies somehow the liberation of magnetic energy due to triggering of a reconnection.
It's very noisy.
Yeah, we can hear you twice, so I don't know if you're using your cell phone.
Is it better?
Yes.
Just a second.
Sorry, really sorry. Bruno, I would like to know if what's triggering the event of the flare, the magnetic reconnection, release of magnetic energy, is some instability related to this accumulation of the winding or the helicity in these active regions.
Yes, I mean the precise mechanism that generates the flares is actually not well known, but we do know that it's related with magnetic reconnection that leads to the reconfiguration of the magnetic morphology around the region where the flare occurs. But also there are several suggestions of instability that may be associated with these events, such as the kink stability, the torus stability. But currently, there are no clear indications of which of these instabilities take place on the onset of flares. But yeah, we do know that it's related with magnetic reconnection.
Right, but it seems you have a very compelling evidence that whatever this mechanism is due to the accumulation of the helicity.
Yes.
Or
Yes.
all right. I have another question. Is
No, just one comment,
right.
because both these quantities, the helicity and the winding, are measures of the complexity of the magnetic field configuration. So if you think of the types of configurations that may lead to magnetic reconnection, you realize that the more complex is the topology of the magnetic field configuration, there's more likelihood of magnetic reconnection to occur.
Right. And I have another question. It seems to me that from the observations, it seems easier to get this potential component of the magnetic field. Is it correct? Is it more?
No, it's very easy because you just
To get the other.
they're both easy because when you get one, you get the other. Because you just in order to calculate the potential part, you just take the radial component, and then you calculate from it, you derive from it a potential, and then you get the other two components. And once you
I
get
see.
you solve a Laplace equation, you solve a Laplace equation for the potential, and then you and then you just subtract BP from B, and you get the current component.
Right, from the same observations, you can get both. So
yes.
I would say the error or the uncertainty would be the same for both, because I think it's important because you are subtracting them.
Yes.
Okay.
Yes.
Okay. Thank you.
Go ahead, Professor Elizabeth.
Oi, Breno. Tudo bem?
Tudo bem.
Breno, I've lost the beginning of your presentation, and but I have a question with regard to boundary conditions, because you know, magnetic helicity is something that in principle should be conserved or advected from another region of the sun, for instance, the solar interior, because this, you know, there is a dynamo action that is related to the formation of these flux stubs, right? And the flares as well. So my question is, how did you account for the effects of the inner boundary, or in other words, the convective zone of the sun, where all these processes are amplified and the dynamo action does take this occurs, and also this transport of
so from observations, it's not possible to do this because we just observed the magnetic fields that have already emerged. But in simulations, we do where is where? Oh, sorry. Here. So yes, in simulations, what we did in this simulation in particular is to set an initial condition which consists of a twisted configuration of magnetic field lines placed horizontally and just below this plane that represents the photosphere. And then we let convection act on this flux, on this tube of magnetic field lines. Then the convection will distort this magnetic flux tube, and eventually it will emerge. So so in this sense, we do have effects of the convection here.
And what was if I may ask another question, what did you impose as upper boundary condition in this case? Outflow boundary, potential
Yeah,
conditions?
yes, in this case is yes, it's no outflow. Yeah, yes.
Potential, yeah.
Yeah, yeah.
Yes. Right. In order to
And,
get, yeah.
Yes, but then we calculate this quantity just as we calculate on the observations, because we wanted to compare because of course we can calculate both helicity and the winding from the volume on the simulations, because we have data from anywhere we want. But when we perform the calculations on observations, we have the magnetic field line sampled only on the surface. So we calculated this only from the surface, which means that we calculated the flux of this quantity, and then we integrate the flux from the start up to the, for instance, here we start calculating the flux here, then the flux is 0, and we integrate the flux up to the time t.
Right.
So
yeah.
So this we do because we want to compare with the observations that I mean, we have observations only on the surface.
Right. Yeah, the active regions in the solar corona, for instance.
Yes. Yes.
Okay.
Exactly.
Great. Very interesting, Breno. Where are you now?
In Durham, that is in England.
Oh, in England. Okay, great. Have a nice day there.
Thank you.
Thanks a lot. Ciao.
Thank you, Professor Becci. Professor Reinaldo actually has his hand raised again, so you can go ahead.
Thanks. I have two more questions. I don't know, is still regarding the uncertainties that you have from the observations, because I understand that you get the data from satellite images. I don't know, but do you have all the information you need to reconstruct the field to obtain these winding measurements, or you have to assume something that maybe it implies an uncertainty in your measurement?
Yes, there are uncertainties related with the measurements, which are of the order of 20 Gauss, I think. So in actually what we did to calculate this for here, this is calculated from observations. So what we do here is to take into account only regions of the active region where the magnetic field is above this threshold, and we also did tests perturbing these with noise, and it actually I mean that it can change slightly the level of the curves, but it doesn't change the conclusions. So, but you're right. I mean, there are errors associated with the measurements.
Right. And I have another question. I didn't not pay attention too much about the time scales of the events between the amount of winding that you have and the emergence of the flare. Can it be used to predict the flares with some hours of?
Yes, we at least from what we observe in this pattern, that we show here, for instance, for the most prolific active regions in terms of number and intensity of the flares, we see this pattern of very strong input here, and then it's followed by the start of the activity. And here it precedes the start of the activity by about I think 15 to 20 hours, and between this peak of input of current carrying winding, there's more or less I think about 60 to 70 hours. So I mean it's I think it can be used at least as an indicator of very I mean of a very likely intense flares to occur. And also we see here on
Very
this, the
interesting.
other one, on the other one, it takes about, I think, about 100 hours between these and the two consecutive intense flares, the 2x class flares here. So,
I guess this kind of prediction is very important for space exploration or instruments.
Yes, because yes, I mean it can damage satellites and other, and also telecommunication, all sorts of problems related with these events. So it's very important to predict them.
Thank you a lot.
Thank you, Professor Reinaldo. Breno, I actually think I can follow up with a question of my own. I was going to ask something very similar to what Professor Reinaldo said. And the question would be, okay, we have this kind of time interval that we have of 100 hours, or I don't know, something along those lines, in order that we have before the occurrence of the flare. So what would we need in order to actually predict this kind of events on a regular basis? Do we need some kind of other instrument, or can we do with the data that we have now? Do we need another instrument to have a high cadence on our observations? What would be necessary, or is it already possible?
Yes, I think the cadence, because the cadence of these data sets is 12 minutes. So it's we sample the magnetic field, the measurements each 12 minutes. From here, I mean, there's a problem here, because from here we observe only there are measurements available on the magnetic field of the active regions only on the side of the sun that we can see that is towards us. So suppose that there's an active region emerging on the other side of the sun that we don't observe, and then it could be that there is an input of this quantity here on the other side of the sun, and then the flare occurs on the side that is towards us. So this could be a problem. So yes, if there's something that could be improved in terms of this, is to have at least more a way to measure the magnetic field lines more evenly throughout the sun. And of course, this work was published actually last week. And after this, we tested several other active regions, and at least for this, the intense flares, this pattern repeats. I mean, we see the same pattern for every active region that presents an X-class flare. But in terms of M-class flares, the thing gets a bit more messy. I mean, it's not so clear. But okay, I think at least there's a strong indication that this type of analysis can help us predict at least the most intense ones.
I see, thank you. And now Professor Laerti actually has a question. Go ahead, Professor.
Hi, Breno. Nice work.
Hi.
Congratulations. Actually, my question is more in the academic side than the scientific one.
Yes.
What or how did you manage to migrate from geophysics to astronomy?
Actually, I don't know if I migrated, but when I did my PhD, I actually was interested in MHD because I wanted to study geodynamo, and so I actually ended up applying the things that I was studying, which was I was studying MHD waves, so I ended up applying this to the sun, and then I actually ended up doing more research on the sun. But in fact, I also did a postdoc on the the Department of Atmospheric Sciences at IAG, so I actually did a bit of everything in the institute. I did a bit of research in geophysics, a bit in astronomy, a bit in atmospheric sciences, and I don't think I migrated because I still do research on the others too. So, but my main subject, but my main subject now is the sun.
Okay, that's interesting because we don't have too many people with such a broad approach to research. Huh? That's interesting.
Yeah. I mean, because I think my philosophy is that I try to go back to the physical principles that are behind the phenomena, and actually there's much in common between the areas. So that's how I ended up doing, research in all three areas, because I especially in fluid dynamics and in MHT, which are the topics that I studied. So it ended up being useful for all the areas. So why not?
Yeah. Okay, thank you.
Thank you, Professor Larch, for your question as well. And I think there are no more questions here in Google Meet, neither on YouTube. So I think we can finish the presentation. And I thank you again, Breno, on behalf of the Institute and on behalf of the organization. And thank you, all of you here at Google Meet and on YouTube as well for watching the seminar by Breno, and see you next week.